All right, so what I'm going to do today is I'm going to finish talking about 4.4, because there's probably some questions you guys have about it. So I'll go through this discussion, then I'll open it up to questions on the homework, and then we'll start reviewing. All right? So let's finish, because I didn't quite get through the measures of central tendency and variability for a binomial random variable. All we talked about was actually doing the formula, finding the probability for one specific event. Okay. So here's kind of where we ended yesterday. We talked about this physical fitness test where only 10% of adults could pass it. And it asked us to find the probabilities for each of the 5 cases where nobody passes, 1 person passes, 2 people pass, 3 people pass, and then finally all 4 pass. All right, so you'll notice that the most probable event is that none of the 4 will pass. See, it has a probability of 0.6561. And actually came up with these in class, right? We did this at the end of class yesterday. What I want you to notice here is that if I sum together all 5 of these, it's going to equal 1. All right? This thing's pulled out. Okay. All right, so that's something I want you to notice. Now, I could ask you the question, what's the probability that at least 2 people will pass the test? Which at least 2 means 2 people pass, or 3 people pass, or 4 people pass. So when I ask you that, when I say x is greater than or equal to 2, what you do is just add together each of these 3 probabilities. All right? There's no formula for the less than or equal other than you just add together each individual event. All right? If I said, what's the probability that at most 1 person will pass the physical fitness exam, it'd be this probability plus that probability, which is really pretty high, right? It's over 90%. So we have a 90% chance that at most 1 person will pass this physical fitness test out of 4. Okay? That's what this is talking about. So this is a nice review. We dealt with this formula, right, where it's n, choose x, right? So this is the number of events, that's the number of successes. This is the probability of success to the number of successes times the probability of failure to the number of failures. All right, so we'll talk about this more and more. So I'll finish out this section, we'll look at another example. But something I want to talk about is, what is the average number of people that will pass this test? If I ran this experiment with 4 individuals 1,000,000 times, what's the average number of people that are going to pass? Right? And that's listed down here in the next example. So if I said, what's the average x I'm going to get if I did this experiment 1,000,000 times? Right? And here's how we do it. Okay. Calculate mu and sigma, calculate the mean and the standard deviation, respectively, of the number of 4 adults who pass the test, and interpret the results. From section 4.3, we know that the mean of a discrete probability distribution, that's our expected value, right, is the sum of the random variable times its probability. So the random variable times its probability, no matter how many different random variables there are, right? Now, if we go in here and follow this procedure here, it's our x value of 0 times its probability, which is 0.6561. So you notice that the coefficient in front of the parenthesis is the number of people who pass the test. All right? So 0, 1, 2, 3, 4. So it's 0 times its probability, plus 1 times its probability, plus 2 times its probability, and so on, right? Just like our expected value was. Now, the nice thing about this is what ends up happening is this number, 0.4, is simply equal to the probability of all 4 people passing. We see that because these are all independent events. So the average is going to be 4 times 0.1. 0.1 times 0.1 times 0.1 times 0.1. Which is really a pretty simple interpretation. Notice that's just the number of trials times the probability of success. That is the formula for the average. The number of trials times the probability of success. Thus, in the long run, the average number of adults out of 4 who pass the test is only 0.4. So that number is closer to 0 than it is to 1. Right? The relationship mu equals NP holds in general for a binomial random variable. So since our average number of people who pass the test is actually closer to 0 than 1, I would expect my probability of 0 to be the greatest. And it is. Right? And we'll see this throughout these binomial experiments. Your average is going to be right around whatever event has the highest probability. Right? Which makes sense. That's what's going to be the most prevalent thing to happen. So our average number of successes is only 0.4 out of 4. Okay? Now, so that's mu. Mu is equal to n times p, the number of trials times its probability. What about sigma? What's our standard deviation? So in the past, like from section 4.3, right, we found the variance where we had to do the subtraction. It was somewhat of a complicated formula. The formula for standard deviation for binomial is really simple. It's basically mu times q. It's n times p times q. So it's the number of trials times the probability of success times the probability of failure. And here's the derivation of it. This is how they come up with it. So it's the sum of the squared differences times the probability. And as they go through all this derivation, notice they get to this point, 0.36, which is equal to 4, which was the number of trials, times the probability of success, times the probability of failure. Therefore, my formula for variance is n times p times q. How do I find q? Again, do you remember? 1 minus p. It's the complement of success. If you're correct 20% of the time, then you're incorrect 80% of the time, right? If p is 0.2, q is 0.8. So that when you put p and q together, it always needs to equal 1, right, when you add them. And then if variance is npq, then standard deviation is simply the square root of n times p times q. Right? So that is a much simpler formula than any of the variance formulas we've saw up to this point. Right? The other ones we had the sum of x squared minus the sum of x squared over n divided by n minus 1. This isn't nearly that complicated, right? And these values will be given to you in the question. You just have to pick out the right value and plug it in the correct place. So it's the number of trials, how many events are there, times the probability you're successful, times the probability you're unsuccessful, or you fail. All right? So what I want to get out of this is, for a binomial random variable, mu is always equal to n times p, which is the number of trials times the probability of success. The variance is n times p times q, which you'll notice is just mu times q, right? The average times the probability of being unsuccessful. And then the standard deviation is simply the square root of the variance, which is the square root of n times p times q. So all we need to know really for all of these is how many times are we performing it and how often are we correct, right? What's our probability of being successful? That's it. Note the relationship sigma squared equals npq holds in general for a binomial random variable. All right, and then I can go in and construct my intervals, right? Mu plus or minus 2 sigma. So since sigma is 0.6 and mu is 0.4, right, it's 0.4 plus or minus 2 times 0.6, and it creates that interval. negative 0.8 to 1.6. So what random variables fall within this interval? What values for x fall within that interval that I described on the previous page, right? Which of these events fall within the interval negative 0.8 to 1.6? Just 0 and 1. So I would add together the probability of 0, and then I'd add together the probability of 1, and get a really big number, right? Something over 0.9. 0.6561 plus 0.2916. 0.9477. Now what did the empirical rule say for 2 standard deviations? Not Chebyshev's rule, the empirical rule. 95, right? It's 68, 95, 99.7. 68, 95, 99.7. This one definitely falls within that because it's 90.9477, which is 94.8%, which is very, very close to 95%. So I would say it does fall into the empirical rule. And it definitely falls into Chebyshev's rule, right? Because Chebyshev was only 75%. But it actually fits a stronger distribution. Oh, that's weird. There's no space right here. See that? Put it all as one word, basically. So here, adding those two together, we get 0.9477, which is approximately 0.95. The result is closer to the value stated by the empirical rule. The empirical rule says now this is approximately normal, right? In practice, researchers have found that the proportion of observations that fall within 2 standard deviations of the mean for many skewed distributions will be close to 0.95. So this one is slightly skewed, but it's still approximately normal as well. A distribution can be both. It is possible. And then here's our mean variance and standard deviation formulas that I've already written on the board over there. So mean is NP, variance is NPQ. All right. Okay. Let's look at this next example, because what it does, on your homework you're asked to do less than, not just strictly equal to. But it pulls up these appendixes in the back of the book. Now the nice thing about these charts are these are cumulative. All right, that means it's all the probability, it's basically adding together the probability of 0, 1, and 2. If my probability of success is 0.1, then my K, if my K is 2, then that would be 0.93, right? So my P is 0.1, but this is only for 10. Remember our one we just looked at, there was only 4 individuals, right? That's why this number is a lot lower than the one we just looked at for the physical fitness test. Here there's 10 trials. What's the probability of 2 being successful in 10 trials if my probability of success is 0.1? Now this is at most 2, so it adds together 0, 1, and 2. So this is nice that you don't have to go in and do the whole formula for K being 0 or X. K and X are being the same thing. This is the number of successes is K. Because you look down here, all right, probability of 9 is 1 because it adds them all together. Right, if my probability of success is only 0.1, then the probability of all these other things are going to be pretty small. Notice my probability of not getting any successes, if my probability of success is only 0.1, is 90%. I have a 90% chance that I will have no successes out of 10 if my success rate is only 1%. That's what that's saying. And this is cumulative, so it just adds together everything above it. So let's look at an example of where we're going to use this. This is nice because now we don't have to do the formula every single time and then add each of these numbers together. Does that make sense what this is doing here? A little bit. So let's look at this. So what the chart shows for say k is 1 is it shows 0 plus 1 in this slot. So it shows 0.9477. So it's adding together all these values. All right? It's cumulative. That's what cumulative means. Okay? Okay. So there's that for n equals 10. So you need to pick the right chart. And these are in your textbook. But when you click on your homework, it pulls these charts up, right? So this is what the chart shows. Table 2 actually contains a total of 9 tables. There's 9 tables back there with different n values, different number of trials. So if I have 5 trials, 6 trials, 7, 8, 9, 10, 15, 20, and 25, all right? Respectively. In each of these tables, the columns correspond to values of p. So my probability is in the columns, and the rows correspond to the random variable x, the number of successes. So whenever I ask you what's the probability that x will be less than or equal to 2, that's the probability that x is 0, plus the probability that x is 1, plus the probability that x is 2. The nice thing about this chart is we don't have to go in and do that formula 3 separate times and then add it together. Right? Because that's really the only way we can do it. There's not a formula for the less than or greater than stuff. Less than or greater than is simply just the addition of each of the random variables that fall below or equal to 2. Okay? So here it says, notice the probability that x is equal to 2 from the chart would be the less than or greater than 2, less than or equal to 2, minus less than or equal to 1. Does that make sense what's going on here? So it's isolating the probability that x equals 2. So this one, we could find this number by punching it into the doing it into the calculator using our formula. So what it does is it takes the probability that x is less than or equal to 2 minus the probability that x is less than or equal to 1. So what this is doing is isolating just where x is equal to 2. So we get 0.194. This is the probability of exactly 2 successes. This 0.93 number is the probability of at most 2 successes. We see the difference between that, exactly and at most. Right? They're very different statements. And this stuff will come from the chart, from Table 2. All right. Okay, so let's look at this example right here. So this is all in general, basically, from the chart. So notice this. The probability that x is greater than 2, so that means 3, 4, 5, 6, 7, 8, 9, and 10, is just 1, the universe, minus the probability that it's less than or equal to 2. Right, does that make sense? That's like its complement right there. So it's 1 minus 0.93, so then the answer would be 0.07. Which means there is not a very good chance of having more than 2 successes, or 3 or more successes. Does everybody see those two things are equal? More than 2 and 3 or more is the exact same amount of successes, right? More than 2 excludes 2. 3 or more includes 3. Right? And then all the probabilities in Table 2 are rounded to 3 decimal places. Thus, although none of the binomial probabilities in the table is exactly 0, some are small enough to round down to 0, like this one. The probability of no successes in 10 trials, if my success rate is 0.6, I'm correct more than half the time. So I would expect me, out of 10 trials, I would expect 6 out of 10 to be the highest number. So my probability of never being successful out of 10 when I have a 60% success rate is very, very low. You wouldn't expect that to happen. Basically, another way to think about that is, if we had 10 consecutive days with a 60% chance of rain, and it didn't rain on any of those 10 days, this would be the probability that would happen. So one of those 10 days that has a 60% chance of rain, it's going to rain. It has to. I mean, that's just law of averages. I know you guys have heard that term before. That's what law of averages means. Okay? But this is exactly equal to 0. This is no less than or greater than. All right, let's do some examples of this. Suppose a poll of 20 voters is taken in a large city. The purpose is to determine X, the number who favor a certain candidate for mayor. All right? So my random variable X is either success or failure. Do you favor or do you not favor? How many of those 20 say yes, they do favor? How many of those 20 say no, they do not favor? All right? So this is definitely a binomial probability experiment. Because X, each of these 20 voters can only give one of two answers, right? Success or failure, or favor or not favor. Suppose that 60% of all the city's voters favor the candidate. So that's P. 60% of all the voters, that's P. That's my probability that a given person will favor the mayor. Right? Not use this wet erase. So we have, so for part A, it says find mu and sigma. All right? For this experiment, I need to know N and I need to know P. How many trials are we conducting? What's the probability of success in the trial? So how many trials are we conducting? 20. We're asking 20 people. What's the probability that they will have success or favor the mayor? 0.6. So mu is simply equal to 20 times 0.6. Which is 12. Right? What you guys got? When you do 20 times 0.6, you get 12? Yes. All right. Okay. So that means if I conducted this experiment 1,000,000 times and asked 20 people 1,000,000 different times, 20 different people, but eventually some of those people would be the same, I would expect 12 of the 20 to favor the mayor. Does that make sense what's going on there? So now let's find the standard deviation. The first thing we have to do is find the variance, which is N times P times Q. But I already know N times P is 12. So I could just put 12 times Q, but I'm going to go ahead and write the whole thing out. So it's 20 times 0.6. What's Q going to be? 0.4. 0.4. The probability of not favoring the mayor. So it's actually 12 times 0.4. It's going to be what? What's a decimal, huh? Pretty big variance here. What is it, 4.8? Yeah. So, but that's my variance. That's not the standard deviation. What do I need to do to find the standard deviation?
Square root it.
Square root it. So the standard deviation is equal to the square root of 4.8, which equals 2 point something. Let's just do 2.19. Because it was 2.190, right? So my mean is 12 voters. My standard deviation is 2.19 voters. So if I was to construct a 1 sigma interval, right, it would be 12 minus 2.19, comma, 12 plus 2.19. And I'd determine what percentage of all my trials fall within that. All right? The number of voters polled is presumably small compared with the total number of eligible voters.
Thus, we may treat x, the number of the 20 who favor the mayoral candidate, as a binomial random variable. The value of P is the fraction of total number of voters who favor the candidate. Therefore, we calculate the mean and variance. So let's make sure we got these right. And there we go. So we get mu is equal to 12, 20 times 0.6. Variance is equal to n times p times q, which is 4.8. And sigma is the square root of 4.8, which is 2.19. So that's our standard deviation. Okay? Following along there, those are actually really simple formulas for the mean and standard deviation, right, compared to the other ones we've seen. Okay. Now we need to answer the next question. It asks us to find the probability that we'll have less than or equal to 10 successes. So, what's the probability that of these 20 people, at most 10 of them favor the mayoral candidate? So that means we have to consider when none of them favor, when only one favors, when two favors, when three, all the way up to 10. Now, our binomial probability formula only deals with equals. This one we could use our formula when it's just equal to 11. We can't use the formula for inequalities. Because if we go back and look at the formula, notice it says it has x equals the number of successes. It doesn't say x is less than or equal to a certain number. It's strictly equal to. So to answer that question, we would have to do the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2 all the way up plus all the way up to the probability that x equals 10. So we'd have to do this 11 different times and then add them all together. That's why we have the tables. Because that's what this question is asking. Write this one on page 202. Yeah, this question is asking for, find the probability that x will be less than or equal to 10. The probability that x is less than or equal to 10 is equal to the sum of all the strict probabilities, right? So this would take us a while if we had to do it this way. That's why it's nice that the chart is cumulative. The chart shows us. So when it shows 0, it shows us this probability. When the chart has 1, it's actually this one plus that one. When the chart says 2 successes, it's actually this one plus this one plus this one. All right, we kind of see what's going on there? So let me go flip to it. Let me get the right page first. It's Appendix A. And if I ask you to do this on the test, I'll give you the chart. Okay? I wouldn't expect you to memorize that chart. Degrees of freedom. It's in Table 2. Okay. 765, yeah, that's where it starts. So page 765. Tabulated values are the sum of the probabilities from x equals 0 to k. So the formula only tells us each of these specific bars. Right? The chart tells us the sum of all the bars. Right? That's the difference between the two. So for our experiment, what's n for this one we're trying to answer? How many trials are there? 20. So I need to go find the chart where n is 20. Okay? So let's flip up, n 8, 9, 10. Next page, 15, and there's 20. Does that make sense? Right there, finding that? Okay. What's our p for our experiment? 0.6. So I'm going to ignore all these other numbers except for the values that are right here in the column 0.6. All right? Now you'll notice that the probability that they'll favor the mayor is actually pretty high, right? I mean, 0.6 is relatively high. It was 0.6, right? Yeah. So it's probable that if you just randomly pick somebody, they're more than likely going to favor the mayor as opposed to disprove, right? Because it's 60%. So that's why values that are really low. So the chances that none of the 20 people will favor the mayor is practically zero. There's basically no chance, if you randomly select 20 people, that none of them will favor the mayor. If you do find an event like that, that's an outlier. That's an anomaly. That's something that you wouldn't expect to happen. It's very unlikely. You'll notice the numbers really start gaining in here, right? So notice from here to here, it's basically 0.2 is the difference. From here to here is basically 0.2. So it's almost going up 20% as we get this 8, 9, 10, 11, 12. So right here, notice it's basically hit 1 if we add together all the probabilities. And then out here, the number's not getting big very fast because you wouldn't expect to find 18 out of 20 favor the mayor. So to answer our question, it says x is less than or equal to 10. That's this value right here. The chances that we will find less than or equal to 10 favorable people is only 0.245, or basically 25%. All right? You'll notice it really jumps above. Oh, I was pointing at the wrong column when I said add 0.2. That was at 0.5. Because notice how small this number is, and then when we get to 11, it basically doubles, and then it adds 0.2 on again. So right here at the 10, 11, 12 is really where it's adding in most of the probability. Do you kind of see what's going on there? What's happening? So to answer that question, it says B, use Table 2 of Appendix A to find the probability that x is less than or equal to 10. That answer, this is a cumulative distribution. So this number is 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way added together to 10, which is 0.245. Okay? That was 767. I'll come back to that. So the answer to part B, the probability where x is less than or equal to 10 is 0.245. Another way to think about that is our chances of getting less than or equal to 10 favorable people, if we'll get less than or equal to 10 people who favor the mayor, is only a 25% chance. And that includes 0 people favoring, 1 person favoring, 2 people, all the way up to 10. Okay? So let's look at part C. Part C says strictly greater than 12. That does not include 12 people. Does everybody see that? That's only greater than 12. So that's the probability of 13, of 14, of 15, of 16, of 17, of 18, of 19, and of 20. Okay? So let's go back to that. All right, so the probability that x is less than or equal to 10 was 0.245. The probability that x is greater than 12 is equal to, according to what our book said, right, which was on page 202. Let me go back to that real quick. See what it says for the greater than stuff? It's basically the universe, which is 1, minus the probability that you're less than or equal to that number, right? So for this one, what would it be? It'd be 1 minus what? The probability that x is what?
584.
No, I'm not asking for the answer. I'm just rewriting this greater than symbol in terms of 1 minus the less than or equal to. So what is this going to become now? If it's x is greater than 12, the opposite of greater than 12 would be x is less than or equal to 12. Right? Does that make sense? So the probability that it's greater than 12, right? The opposite of greater than 12 is less than or equal to 12. Right? You guys see that? Because if I take all the numbers that are greater than 12 and add together all the numbers that are less than or equal to 12, I have all the possible values, right, of our random variable. So what is the probability that x is less than or equal to 12? Let's jump back to our chart. Here's 0.6. There's 12, so it's right there. 0.584. 1 minus 0.584, which is equal to 0.416. Which basically means our probability that more than 12 people will favor the mayor is 41%, or 42% actually if you round it to the highest percentage, which is still pretty high. Right? That's a pretty high number. And if we go back here, we use the fact that for all probability distributions, the sum of all the x of the probability for every x is equal to 1. Because we will hit one of those events. It has to happen. Either nobody favors the mayor, or 20 people favor the mayor, or some number in between. Right? There can't be -1 people that favor the mayor. There can't be 21 people that favor the mayor. So the probability that x is greater than 12 is equal to 1 minus the probability that x is less than or equal to 12. And the reason I convert it to this is because the chart tells us less than or equal to. The chart doesn't tell us greater than. It could, I mean, in the way that they wrote the chart, there are some charts that tell us greater than, but not this particular one. So this is my probability that I'll have less than or equal to 12 people that approve of the mayor. So the probability that I'll have more than 12 is the opposite, 0.416, or the complement of 0.584. So the last part says find the probability that exactly 11 voters favor the candidate. I'm going to do it by the formula, and then we'll check it from the chart. Okay? So let's do it using the formula first. So n is 20, p is 0.6, so this is d. So find x equals 11. The probability that x equals 11. So this is exactly equal. So I can use the formula right here. Right? So the probability, so from the formula, the probability that x equals 11 is equal to 20 choose 11. So how many different ways can I pick 11 people out of 20? Times the probability of success to the number of successes times the probability of failure to the number of failures. If 11 people approve, how many disapprove?
So, 20 minus 11.
Right. Which is? None. So put that in your calculator. Do not try and do that in your head. So we have 20, and let me zoom in so we can make sure we know how to punch this stuff in the calculator. So it's 20, I hit the PRB button, and go down to NCR, choose 11, and hit enter. So that's how many different ways we can choose 11 people out of 20. 167,960. Thank goodness we didn't have to list all of those, right? So now I need to multiply that number times 0.6 to the 11th. So my probability of success times to the number of successes, not times, to the, times my probability of failure to the number of failures. Everybody following there? So 0.6 to the 11th times 0.4 to the 9th, and hit enter. And let's do it to 3 decimal places, since that's what the chart gives us. So what is this number to 3 decimal places? 0.16. Or 0.160, but we'll just write it as 0.16. So now let's do it from the chart. So the probability that x equals 11 is going to be equal to the probability that x is less than or equal to 11 minus the probability that x is less than or equal to 10. Everybody see why that works? It's because the chart tells us at or less than, right? So if I want to know what it is exactly at 11, I need to know the probability that it's less than or equal to 11 minus the probability that it's any number less than 11, right? That it's, so basically this is counting probability of x equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we're taking off the probability that it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So all this is leaving behind is equal to 11. You guys see that? What's going on there? So let's do that in our chart. What is it? Let me flip back and look at it. And we better get the same number, right? So the probability that x is less than or equal to 11 is right there, 0.404. 0.404 minus the probability that x is less than or equal to 10 is 0.245. And we're going to have a little bit of a rounding issue because all of those numbers have been rounded to 3 decimal places, right? So now I want you to do 0.404 minus 0.245. And what do we get? 0.159, which is exactly the same as this if it was rounded to 2 decimal places. So really here I would probably put, for both of them I would put approximately, right? Because they're both approximations. You guys kind of see what's going on here? What's happening in these charts? So this is a way to come up with the exact same values. It's just the chart tells us the cumulative distribution, which is really nice because if we didn't have the chart, the only way we could find this out or this out is to count each individual one, do our formula each time, and then add them together, which this is much easier, right, looking at this chart right here. Okay? All right. There's that. So, at this point, I will open it up to questions about the homework. Anybody have questions about the homework? Yeah.
Mine came from 4.3.
Okay.
Every time I try to do one of the variance formulas, I screw it up.
Which is probably an order of operations thing. So let's go look at it. Once again, remember, I am not testing you over this assignment. I'm not testing you over 3.5 and 3.6. I'm not testing you over the conditional or the independent stuff. All right? I went over it so that this binomial stuff would make sense because all of these trials have to be independent, right? What happens in the first one has nothing to do with what happens in the next one. Okay, so 4.3. Do you remember what number it was, Mark?
All of them have variance.
Oh, okay. All right. It probably is an issue then with your order of operations. Because this one deals with expected value, right? Okay. So we can do this one. Yeah, let's do this one. So let me snip it out. Now, an issue 2 might be if you use the rounded mu value in the variance formula, there might be an issue with that, so let's go and look. because the variance formula uses mu, right? You subtract mu squared. Okay. Consider the probability distribution shown here. So here's each of my events. So x can be 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 different outcomes. All right? 9 different outcomes. This is definitely not a binomial experiment, right? Because for binomial, there's only 2 outcomes, success and failure. So this says calculate mu. So think back to 4.3. What's our formula for mu? For any discrete random variable. We remember? We saw it today when we were talking about the binomial stuff for mu. Right. Sum of each value times its probability. Right? So mu is equal to the sum of x times p of x. Right? So this equals -4, and I'll put the parenthesis around the probability, not 0.4. -4 times 0.01 plus, or minus I'm going to put since it's a negative, -3 times 0.08 minus 2 times 0.09. Well, yeah, because it's plus a negative.
Oh.
Because each of those are negatives. So I could have put plus -3. Right? Which is easier just to put minus, right? -1 times 0.16. Now I'll do plus. Plus 0 times 0.29. Plus 1 times its probability, 0.18. Plus 2 times 0.11. Plus 3 times 0.06. Plus 4 times 0.02. So mu equals, and it says round to 2 decimal places. So let's do that in your calculator. So negative, and I'll go ahead and show you guys how I do it. You don't need any parentheses here. That's the nice thing about these expected values. It'll do all the multiplications first, and then do the addition and subtraction. So 0.4 times 0.01. I could go plus a negative, but I'm going to go ahead and just do minus 3 times 0.08, minus 2 times 0.09, minus 1 times 0.16, plus 0 times, which I don't even have to, plus 0. This one I really don't even have to do, but I'm going to stick with the formula. Because it's not going to add anything, right, when I multiply by 0. Plus 1 times 0.18, plus 2 times 0.11, plus 3 times 0.06, plus 4 times 0.02. This distribution could really be assumed to be, say, where the random variable is the number of inches you are from the average height, is a way you think about this. Now, I don't know where the data came from. This is just something I'm kind of tying to it. So the probability that you will be average height is 29%. The probability that you'll be 1 inch taller than average height is 0.18. So you notice as this number gets really big or really small, the probabilities go down. Because those are shorter people and taller people. That's one way to think about this. I don't know where this data came from. But that's kind of what it could represent. So this tells me what the average height is of any individual, right? Where 0, or the average number of inches, they're less than or greater than the average height. So 0.04. So on average, people will be slightly taller than average, right? 0.04 is my mean, is my mu. So let's go back here and make sure it's correct before I move on. Okay, good job. So there's our start. Of course, you can't see that because I got the document camera. So I put in 0.04. Okay, good job. All right. So now we need to find the variance. What's the formula for our variance? Well, I'm going to hit view an example and go to it.
-4 squared times 0.01.
Right, and this one doesn't have the shortcut like I wanted.
That one up there on the example looks different than what you did in class.
Well, yeah, because what I did in class is the shortcut for it. They're equal. Just like how the regular variance formula has the long one and the short one, it's the same thing with this. You don't like that one?
Not on
I think that's all zoomed in. Okay, so let's go to the next page. So right here. What the view and example gives us is this first formula. This is what the view and example gives us. But it can be shown that it's explicitly equal to this formula. Now, I like using this one because what I can do is go back in my calculator and add in squares. Right? Because when I did mu, right, when I found the average is without that x squared value, right? It's just sum of x times p of x. So what's nice about this formula is I can go back in and just add in this squared value to each of my observations. And then I'll just subtract off mu squared. So that's the shortcut formula. You will be given that on your exam. Right? And if I ask you to find the variance of a given discrete probability distribution, I'm not going to have 17 different outcomes. All right, there'll be 4 or 5, somewhere you can actually do it by hand. Okay? So, the variance is equal to the sum, so we got 0.04 for the mu, so I'm going to rewrite it up here. So mu is equal to 0.04. So variance is going to be equal to each of my values squared. Now I can't go back in and just add the squared because it's not going to square the negative. So I'm going to have to go do it by hand. So it's -4 squared times its probability, which was what, 0.0 something? So I'm going to rewrite this, and then I'm going to flip back to that chart. So let me do that. So variance is equal to the sum of the random variables squared times their probability minus mu squared. You can use this formula, that's fine as well. I like using the shortcut one. And it's even called it right here. And the shortcut formula, see, note the similarity between just the regular variance formula and that one? How there is separate forms of it. So that means my variance is going to be equal to, what problem was this on? Oh yeah, it's a homework assignment. So my variance is equal to -4 squared times its probability, which is 0.01, plus -3 squared. So notice how I don't have -3 squared, because what will happen is it will square the 3 and then attach the negative to it. That's bad. We don't want that to happen. We want the -3 to get squared so that it turns to a positive value. Right? So 0.3, or -3, what's the probability? 0.08 plus -2 squared times 0.09 plus -1 squared times 0.16 plus 0 squared, which doesn't make a whole lot of sense to say, times 0.29 plus 1 squared times 0.18 plus 2 squared times 0.11 plus 3 squared times 0.06 plus 4 squared times 0.02 minus mu squared. Minus 0.04 squared. Now, that is not something you'd want to do by hand. All right, that's definitely something you want to do on the calculator. So this is my sum of my x squared times the probability. So there's my first x value, there's my second, third, fourth, fifth, sixth, seventh, eighth, 9. So there's all 9 of them. Right, there are 9 different outcomes from this experiment. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then finally subtract off the 0.04 squared. It's very important that you put this negative value in parentheses, because your calculator does not interpret this to be equal to, those two things are not equal in your calculator. Now you might think they're equal when you look at them, but why aren't those two things equal? Think about order of operations. What comes first? Exponent or subtraction? This answer is actually negative 16. Because what it does is it squares the 4 and then puts a negative on it. This one's positive 16 because it's negative 4 times negative 4. Does everybody see the difference between those two things? The parentheses make a big difference. Yeah, do that in your calculator and see what happens. So if you just did negative 4 squared, look what it tells me the answer is. As opposed to parenthesis negative 4 squared.
So when we do that formula, we have to put the parentheses over every single one of those?
No, just if they're negative. Yeah, you don't need the parentheses here on 0 or here on positive 1 or 2 or 3 or 4.
Right.
You only need them on the negatives. Yeah, and that's probably most of your issues right there. Because look, I mean, negative 16 and 16 are very different, right? They're not even close to the same number. So that's probably the issue that most of you are experiencing with the variance. So let's go ahead and do the variance formula. All right, so open parenthesis, negative 4 squared. And you don't even need to put the times symbol. You could just do another parenthesis, but I'm going to go ahead and do it. Times 0.01. So that's my first x value. That's my first one of these, right? My x squared times probability of x. Plus. Yeah, I can't write minus 3 squared. That is not going to be correct. It has to be plus a negative 3 squared. Plus, open parenthesis, negative 3, close parenthesis. And then exponent squared times, open parenthesis, what's the probability? 0.08. Plus, open parenthesis, negative, well, yeah, and you can use the minus as well, it doesn't matter. Plus negative 2 squared times the probability of negative 2, which is 0.09. Close parenthesis, plus, open parenthesis, negative 1 squared. Times the probability of getting negative 1, which is 0.16. Plus, now I'm not going to worry about the parentheses. Plus 0 squared times, and you don't even need the open parenthesis, but I'll just go ahead and keep it going. Plus 1 squared times 0.18 plus 2 squared times 0.11. Oh, am I out of room here? So let me go ahead and, so I'm going to delete that and delete that. So I'm going to do this because it looks like my calculator won't let me go any further. So I'm going to go ahead and just hit equals on this part and then just keep going. Right? Because this is, I'll hit equals and it'll basically do all of this, and I still need to do that piece, that piece, that piece, and that piece. Right? So equals. Then I'm going to do plus, open parenthesis, which I don't even need the parenthesis, 2 squared times 0.11 plus 3 squared times 0.06, close parenthesis, plus 4 squared times 0.02. And so that is my sum of x squared times px. That is the answer to this piece right here. That is 2.88, so now I need to subtract mu squared. Notice here the minus is not in the parentheses. We're subtracting 0.04 squared. We're not adding negative 0.04 squared. All right, so make sure, so here you don't want parentheses. So then it would be minus 0.04 squared. What's that rounded to 2 decimal places? And it doesn't take off very much because 0.04 squared is a very small number. I mean, look what 0.04 squared is. That's why it didn't change by very much. It's because 0.04 is so small. I mean, the mean is practically 0. Now, what does it say? How many decimal places do we need? Round to 4 decimal places. Which is exactly what our answer was, right? It was 4 decimal places. So what is it? There it is, 2.8784. So that was probably your issue with the variance, is not putting the negatives in parentheses. So how do I find this, the standard deviation? Just square root it. Right, so I'm going to go second square root, second answer. Oh, no, I'm not going to do answer because I hit equals one more time. Right, that's not going to be correct because right now it's saved this number as answer. So I want to delete answer and type in 28784, 2.8784. So second square root, 2.8784. And then it says round to 3 decimal places, which is what? 697. Round to 3 it says. Not 4 this time. Yeah. 1.697. There we go.
Another one that I have a question on is the bedding one.
That's on this, or is that on 4.4?
I'm not sure.
There was some betting ones on the review. Have you looked at the review yet?
No, I haven't
Okay.
got that far. I'm wanting to say it was either 4.3 or 4.4.
Okay. But, now I could ask you a question. But before we get to that, Crystal, let me ask one more question about this. So what's the probability that x of x plus or minus sigma? What's the probabilities within one standard deviation of the mean? So the first thing I need to do is construct this interval. All right? And then I should rewrite this as negative sigma is less than x is greater than sigma. All right, so and I meant x minus. So what are all my probabilities less than, with one standard deviation below the mean and one standard deviation above the mean? So first let's construct that interval. My x minus sigma and my x plus sigma. X bar, I should say. Or mu, actually. So mu minus sigma is going to be 0.04 minus 1.697, comma 0.04 plus 1.697. So 0.04 minus 1.697 is Negative 1.657, comma, 1.701. Is that right? When I add 0.04 and 1.697? So this is equal to the probability that x equals, is negative 2 in this interval? Would my probability of negative 2 be considered in that? What's my low-hand endpoint of this interval? Is negative 2 to the left of 1.657 or to the right? It's to the left, so it's not considered in there, right? So the values that are in my 1 sigma interval are when x equals negative 1 plus my probability when x equals 0 plus my probability when x equals 1. So my probability when x equals negative 1 is 0.16, plus my probability when x equals 0 is 0.29, plus my probability when x equals 1 is 0.18. So what does that equal? 0.63? 0.63. My empirical rule says 0.68. Right? It has to be within 1 standard deviation. So we're pretty close right here. Alrighty.
So that's on the question where they ask if it falls within the rule and is it within 1 and 2.
Right, right. So then if it said 2 standard deviations, then I would need to do 2 times 1.697 and put that number there, right? So if I had changed this to 2 sigma, then this number would be 0.04 minus 2 times 1.697, right? 2 standard deviations below. Then you have to consider which random variables fall within that interval and add together the probabilities. Okay? Notice on this piece, I don't have the capital P out in front. I'm not asking for the probability here. I'm just constructing an interval. I'm constructing a 1 sigma interval. All right? Okay, let's look and see if I can find the betting one you're talking about. And it's you think it's in point. So which one of these 3 is that distribution? What do you guys think? B. Because the highest probability, the highest relative frequency is the number directly in the middle, and you notice the relative frequencies taper off as you get towards the edges. So it has to be this one. Right? That's the only one it could be. The other 2 don't have the right shape. This one and this one have double mounds, right? Not just one. Okay. So you're not sure if it was on this assignment? Crash testing, dust mite levels on a blade of water. I have no idea what that is. Right here.
That one.
The lottery? Okay. Let's look at this one. Now this is a really cool problem because this is where you really go into the lottery. This is really how you determine your chances of winning the lottery. Or your expected net earnings. All right. The chance of winning a lottery game is 1 in 27 million, which isn't real good, right? I mean, that's basically one person in Los Angeles and New York combined, right? Now, that's probably a little more than 27 million, but pretty close, really. That's about the population of Texas. So 1 person in Texas would win the lottery. That's about the probability. Okay. Suppose you buy a $1 lottery ticket in anticipation of winning the $5 million grand prize. Now, we're not talking about after taxes or anything like that. That would complicate this problem, right? Because they take 38%, right, on gift tax. You only get 60%.
62%. Okay, suppose you buy a $1 lottery ticket in anticipation of winning the $5 million grand prize. Calculate your expected net winnings for this single ticket. Interpret the result. All right? So here we need to multiply our random variable times the probability of winning. Right? So you either win nothing or you win, you either lose $1, which is -1, or you gain 5 million. Right? Does everybody see that? Those are the only two things that are going to happen here. So let's write it out in a chart. Then I'll go back and talk about the view and example, because there's probably some stuff in there that's done a little bit differently that you might not understand. All right, so we have our random variable x, and then our p of x will go over here. All right. Oh, I want to do that right here. No, that's right. Go here. Try to make a nice pretty chart right here. So p of x is going to go here. So that's in this column, and then up here is going to be my x values, all right? So, my two things that x can become, so what are my random variables? What are the two outcomes for the experiment? It's either going to be -$1 when I don't win, so I lose $1 if I don't win, or if I do win, how much money do I win? Not 5 million, you win 499,999 because you bought a ticket for $1. Oh, I know what I need to do. So this is x. And what's my probability of x? So what are my chances of winning? What are my chances of this being the outcome? What does it say? 1 in 27 million. So 1 over 27. 1, 2, 3. 1, 2, 3. Everybody following along where I'm getting this? Because only one of two things can happen. I either don't win or I win. So I could even cast this as a binomial experiment. Right? Success or failure. So if my chances of winning are 1 in 27 million, what are my chances of not winning? What do these two things have to add to? Right, what's left over, right? So when I add this probability and that probability, I get 1. So this is going to be 26,999,999 out of 27 million. Let's go ahead and write those as decimals. So what are they approximately? So what is 1 out of 27 million? 1 divided by 27, 1, 2, 3, 1, 2, 3. It's going to be a very, very small number. 1, 2, 3, 4, 5, 6, 7. Right, 7 zeros and then 3, 7. And then what's this number? 26,999,999 divided by 27 million. It's going to be 0.99999, right? Something. 0.9999963. So my mean is equal to the sum of x times p of x. The sum of my outcome times its probability. So this is going to be equal to -1 times this number, 0.9999963, plus
499,999. Let me write that down, so we have room. Plus 4999999 times this number, 0.000000037. Let me go and look at the view and example. Oh, that's all I want. They have a pretty ugly looking formula because this formula, I mean, the numbers are a little bit different. Right? But it falls through the exact same thing. So, yeah, this is a little harder to follow. If you lose $1, but if you win, you receive $12 million minus the $1 spent on the ticket. Use the formula above to find the expected net winnings for this single ticket value. Right? So what they do is they factor out a number. That's why this is just 1. They factored that value out. So that's a little confusing formula, really. That's probably why you couldn't read that and figure out what's going on. This makes a little more sense, right? Because this follows along what we've done. We find our outputs. There's one of only 2 things that can happen. We can either lose our $1 or we can make 5 million minus 1. So let's punch that in the calculator. So let's do -1. -1 times 0.999999963 plus 4999999 times 0.1234567 zeros 37. And you could do the fractions there instead of the decimals, which might be the better way to do it. But so there it is, -1. So my output times the probability of its output. So more than likely, I mean very, very more than likely, we're going to lose $1, right? We're not going to win this lottery, more than likely. But there is a chance we could win, which is, this is the amount of money we would win times our probability of winning. So hit equals. There it is, -0.815. So for every $1 I bet, I would expect to lose 80 cents. That's what this is saying. This has a negative expectation. Casino games have an expectation just like that. It's negative. The more you play, in the long run, you will lose. Right? So you're going to lose 82 cents. What does it say to round to? It says to the nearest tenth. How many decimal places is that? 1. Right. Oop. -0.8. So our expectation is to lose 80 cents every single time we play. That's our expectation. So, what that really leads you to believe is do not try and use this as a retirement plan. All right? It has a negative expectation. You will lose money. Okay? So your average, would this be losses or winnings? Losses. Your average losses for a large number of games would be 80 cents per game. See, basically, you would almost lose your entire dollar every single time. All right? And this means for a large number, it would be 80 cents per game. So if you played $100, you would lose $80. All right? That's what this is saying. Anytime you have a negative expectation, you want to stay away from it when it deals with money. Now, 80 cents isn't a whole lot to lose on a $1 lottery ticket. That's why people still play. Because, I mean, $1, what's the difference if you lose it anyways? It's not like you're any farther behind than you were to start with when you had the dollar. Right? If lotteries were 20 bucks to get in, nobody would ever get into them. Right? Because your expectation of losing would be far too high. But most people can stomach losing 80 cents. So that's why people still do it. And of course, if we went in and did taxes on this, because of this $5 million grand prize, you probably only see about $3 million of it. So if you considered that into your expectation, that value would get even smaller. Because you're not winning the whole $5 million. Right? You're actually paying taxes on it. So when you consider it that, your expectation goes down even more. Oh, here's a good one. All right, let's do one more. Then I'll cut you guys loose. I'll mention a few things to study. What pages to look at and that type of stuff, but let's do one more example. All right. Suppose a bookie will give you $6 for every dollar you risk if you pick the winners in 3 games of a sport on a parlay card. Now, when you parlay, all 3 have to win. If one loses and 2 wins, you lose. Right? All 3 of them have to hit. So, just think about flipping a coin. What are our chances of guessing a correct coin flip 3 times in a row? Well, your chances of getting it right the first time is 0.5. And then your chances of getting it right the next time is 0.5. Right? And your chances of getting it right the next time is 0.5. But each of those events are independent, right? The fact that it was ahead once doesn't mean it's going to be ahead again. So your chances of just picking 3 coin flips in a row is 0.5 to the 3rd power. There's your probability of just picking 3 coin flips in a row. It's 13%. So that's why parlays pay well, because your chances of winning go down, right? So you only have a 13% chance of guessing a coin flip correctly 3 times in a row, which is really pretty low. Let alone if you do it 4 times, right? And then each time you do it, your probability goes down even more. Picking 4 coin flips in a row is 0.0625. When you pick games on the spread, that basically makes it a coin flip in a sense. The reason they have the spread isn't because that's what the bookies think is going to happen. It's because that's how you get half the money on each side of the line. You want 50% of the money on one team covering and 50% of the money on the other team, using the spread. So one team, you want 50% of the money saying the Broncos are going to win by 7, and you want 50% of the money saying the Broncos aren't going to win by 7. So that no matter which team wins, the casino still makes money. So that in the long run, they have a positive expectation. That's how they set this stuff up. Right? So, suppose a bookie will give you $6 for every $1 you risk if you pick the winners in 3 games of a sport on a parlay card. Thus, for every $1 bet, you will either lose $1 or gain 5. All right? Because he only gives you 6. And one of them was your dollars to start with, right? So you only won 5. Okay. What is the bookie's expected earnings per dollar waged? Note the odds of winning and losing on a particular game are the same. Right? Because if one game was less than the other, that would really affect the odds. We'll just, consider that your chances of winning a given game is 50-50. It's basically a coin flip. All right? So let's say, what are our outcomes for this experiment? What are the possible things that can happen? I can either lose $1 or what? Win $5.
So the bookie's only going to He's either going to lose $5 or
He's going to gain
one.
one. Yep. Oh, so yeah, these are the other way around, huh? What is the bookie's expected earnings? So I do need to switch those around. Because it's in terms of the bookie, not in terms of the wager. Right? Okay. Now I need to see how they write the probability here so that we can, because I think they just might call it P and then P cubed. Oh, what are all the outcomes? Okay, that's how they do it. So if we consider the probability of winning to be the same, so let me explain how they came up with these probabilities, all right? Basically, they take two outcomes, right, and determine how many different, out of wins and losses for 3 games, how many different sets could we get, right, which is kind of like the tree diagram. So we can either win all 3, we can win the first 2 and then lose the third one, we can win the first and third and lose the second one, we can lose the first one and win 2 and 3. And then we can do the ones where we have 2 losses, right? We can win the first one, lose the second 2, lose the outside 2, win the second one, lose the first 2, win the third one, or we could lose all 3. The only one of these situations that the bookie pays out is this one. You have to win all 3 games, all right? Now, on a test, I wouldn't expect you to come up with these probabilities, all right? This I would give you. So I would give you these probabilities, but I would expect you to be able to tell me what the expected value is, okay? So this number, the bookie only pays out 1 out of every 8 outcomes. Does that make sense what's going on here? If these are all coin flips? So the bookie only plays out 1 out of 8. So the bookie loses $5 1 out of every 8, but he gains $1 7 out of every 8. And 1 out of 8 is equivalent to 0.125. And notice how on the calculator I did 0.5 cubed and I came up with this number. Right? It's because each of these games are basically coin flips. There's a 50% chance of you winning. There's a 50% chance of you losing. All right? So if I know the probability that the bookie pays is 0.125, then the probability that the bookie doesn't pay is the opposite of that, right? 0.875. 1 minus 0.125. Now, where professional gamblers make their money is they go in here and find which one of these games aren't 50-50. Which one of all these games we can bet on are slightly skewed, right? Where is the line not correct because they know some inside information, right? Like the quarterback was sick or he got drunk the night before. Because that definitely influences the probability of each of these outcomes, all right? So what's the bookie's expected value here? Well, that's going to be the average. So the expected value of x is equal to the sum. So this E and that sigma are not the same symbol. The sum of x times P of x, which is equal to 1 times 7/8 plus, or actually I'm going to do minus, yeah, I'll do plus. Plus a negative 5 times 1/8. When I do these two multiplications, 1 times 7/8 is 7/8, right? You guys agree with that? What's negative 5 times 1/8? Remember we multiplied fractions yesterday. This is 5 over 1, right? So you just multiply straight across. So negative 5/8. So the answer is 2/8, which is equal to 1/4, which is equal to 25 cents. So what this means is for every $1 bet, the bookie expects to make 25 cents.
So he has a positive expectation. So that means if you're a bookie, you make money. That's why there are people that do it. All right? And it really all comes back to each of those games having an equal probability. If you can pick games where you're more likely to pick the winner, then you skew this expectation. Right? You actually drive it down to a negative number for the bookie. Right? You can actually do this with any sport. But for team games, it's easier because you can put a line where two teams are playing, right, that basically makes it 50-50. It's different than, say, picking an individual sport like tennis or golf, where if you pick one guy to win a tournament, I mean, he's got to beat everybody else in the field, not just one other person, right? That's why it's different than team betting. All right? Because I think the favorite in, say, golf is 6-1. So you'll win $6 for your dollar bet if just picking the one guy. It's just the difference is he's got to beat a whole bunch of people, right? He doesn't just have to beat one person. So that's why the odds go up a little bit. But that's it. That's what the bookie's expected earnings would be. 25 cents. So if you're a bookie here, you want to get people to bet constantly. Because you're expected to make money every single time somebody bets. Now, that doesn't mean you're going to win every time, but in the long run, you will. You'll win 25 cents. So if you had a $1,000 bet, you would win $250. That's what this is saying. Right? Okay. So good one. Note the odds of winning and losing on a particular game are the same. That has to be the case. That means it's a coin flip. 50% chance of winning, 50% chance of losing. So that's why the bookies, you always pick against the spread, right? By, say, if they're favored by 7 points. Because, you know, if the Broncos are playing the Raiders and it's just straight up, you pick the Broncos most of the time and they would win. But that's why they put a 10-point spread on it to basically make it 50-50. That's what the spread does. And for all sports. Okay? So let's go in and look at some review pages. We've got about 15 minutes left. So let's go back to here, open up our multimedia library. Page 168. So your Chapter 3 review material starts on 168. So write that down. Chapter 3 review, 168. Which, your review sheet that's in my math lab, this thing right here, this exam 2 review, is basically what I'm going to go over right now. This is basically the stuff picked out of the end of chapter review and then put on one sheet. And each of these that say NC you will have on your formula sheet. Okay? So let's go look at, and then what the heck, it closed the book? Chapter 3, select all. So 168. 168. Here we go. Key terms. So the stuff with the stars you don't have to worry about, right? Those are the optional chapters. You also don't have to worry about conditional probabilities or independence. All right, independent events. All right, but you do need to know what the complement is. Think about complement as the opposite, right? The complement of winning $1, if you're the bookie, is losing $5, right? So the probability that you'll win is 7/8. Its complement is 1/8. Two values, when you add a value with its complement, it always equals 1. Right? So here's the numbers to know. What does it mean for something to be a random sample? What's the difference between a sample point and a sample space? Right? A sample point is one outcome. A sample space is all the outcomes of an experiment.
A sample space is a collection of sample points. What does it mean? What is the intersection and union? And and or, right? And and or. Intersections and, union is or. And then here's the symbols. This one we don't really have to worry about. The given. All the other ones you should know, though. Set of sample points, probability of an event, union, intersection, complement, number of combinations, and then n factorial. Where the factorial is included in this combinations formula. Right? And I'll give you that formula on the test. So this is on 168. And the next page shows you the probability rules. This is always the case for all of these probability experiments we've been doing. Right? Each of the probabilities have to be somewhere between 0 and 1, which is the case here. And the sum of all the probabilities has to equal 1, which is also the case. Those are our two rules of a probability experiment. It has to happen. Now, it is possible for the probability of something to be equal to 0. It's kind of trivial talking about that, but it is possible. Then there's your combinations formula. We didn't go over this. We didn't go over Bayes' rule. Just ignore that. What does it mean for two things to be mutually exclusive? What does that mean? They have what?
Nothing in common.
Nothing in common. What's the mathematical interpretation of that? They have nothing in common is true, but what symbol denotes in common? Which one of these symbols? Right, in common means both of them have it. Right? That's something they have in common. Isn't that the intersection? Both A and B? So when things are mutually exclusive, their intersection is nothing. They have nothing in common. Their intersection means what do they have in common? Right? Parallel lines are mutually exclusive. They have no intersection. Right? Highway 70 and Avenue O do have an intersection, right? They do have something in common. It's right out here where the stoplight is. So mutually exclusive means their intersection is 0. That's different than independent. When I roll a die and then roll a die again, that's an independent event. But I could get a 2 the first time and a 2 the second time, which means they still have something in common. But the first roll has nothing to do with the second roll. That's what independent means. Which I'm not going to ask you about the independence formula. And here's some other stuff. Just some stuff to kind of think about. In here, independent, I'm not going to ask you about. I definitely will ask you about mutually exclusive. If two items are mutually exclusive, then their union is just equal to the sum of each probability because they have no intersection. If they are mutually exclusive, their intersection is 0. Right? So that piece basically goes away. That's why if they are mutually exclusive, it's just the sum of each of the probabilities. Okay?
If they are mutually exclusive?
It's the sum of each individual probabilities. So see how mutually exclusive talks about the sum and independent talks about the product? Right? But that's the intersection. I'm not going to ask you about this stuff. All right? I would ask you about this, though. This is something you have to know. I would not ask you about this. Okay? I'm not going to ask you about independence or conditional probability. I will ask you about mutually exclusive and complements. Okay? So you can ignore dependence and conditional probability. All right. Let's look at some examples out of this. I wanted to do, yeah, right here. Okay, let's do 154. This is kind of a neat question. Which of the following pairs of events are mutually exclusive? Which one of these pairs of events have nothing in common? If both of the events can happen at the same time, they are not mutually exclusive. So the Tampa Bay Rays win the World Series. Evan Longoria, who used to play for the Rays, I'm pretty sure he still does, I'm not sure, hits 75 home runs. Could both of those things happen at the same time? Yeah, absolutely they could. These are not mutually exclusive. Now, if it said A was the Tampa Bay Rays win the World Series and B was the New York Yankees win the World Series next year, those would be mutually exclusive. Those two things could not happen at the same time. Okay? B, psychiatric patient Tony responds to a stimulus within 5 seconds. Psychiatric patient Tony has the fastest stimulus response time of 2.3 seconds. Do those have something in common? Absolutely. If he does it within 2.3 seconds, then it's definitely within 5 seconds. So these do have something in common. So those are not mutually exclusive. Their intersection is not 0. If that would have said, psychiatric patient Tony has the fastest stimulus at 7 seconds, then they would be mutually exclusive. Okay? A, so part C, high school graduate Cindy enrolls at the University of South Florida. B, high school graduate Cindy does not enroll in college next year. Can both of those events happen at the same time? No, those are mutually exclusive. If this would have said, high school graduate Cindy enrolls in a college somewhere in Florida, then they would not be mutually exclusive. Okay? (158). I could ask you that question. For two events, A and B, suppose the probability of A is 0.7, the probability of B is 0.5, and their intersection is 0.4. So what's the union? What's the probability of the union? What formula am I going to use right there? What's it called? So which one of these formulas am I going to use? Are they mutually exclusive? So we're asking for the union, right? Isn't that what the question was? Are they mutually exclusive or are they not mutually exclusive? Not, because their intersection wasn't 0. So we're going to use this formula. So it's going to be the probability of each minus the intersection, because when I count these probabilities, I'm counting their overlap twice. So I need to subtract off the overlap once. Because here's the probability of A, here's the probability of B. They definitely have an intersection. So when I count each one separately, I'm counting this overlap twice. So I need to subtract it off once. Right? Does that make sense what's going on there? So what is it for that answer? For that question? So right here. So we're looking for the union. So it's P of A plus P of B minus P of A intersect B. 0.7 plus 0.5 is 0.12. Or not 0.12, 1.2. Anytime I add together these two probabilities and I get a number greater than 1, I know they have to have something in common, right? Because the sum of your probabilities can never be greater than 1. So 1.2 minus 0.4 is 0.8. The answer to 158 is 0.8. All right. Okay. Let's look at page 217, the stuff for chapter 4. So 217 is the key terms for chapter 4. Once again, ignore the stuff with the stars. But we covered everything else that does not have a star. What's a synonym for countable? Discrete. The word discrete is a synonym for countable. All right? We haven't talked about continuous yet in this chapter. We're just simply talking about countable things. Look at what happens right here. Really, I would would need to bound this on the upper side by 1 as well. But all the probabilities have to be greater than or equal to 0 and less than 1. And the sum of all my probabilities still needs to equal 1. That's the exact same rules we saw from chapter 3. Right? My probabilities have to be some form of a decimal. When I add together all my probabilities, it needs to equal 1. All right? And then it's got, and we don't use E. You can ignore this one. S is the outcome is a success. F is a failure. P of S is the probability of success. And Q is the probability of failure, which is 1 minus lowercase p. Right? I think this should be lowercase p, not uppercase p. That's a typo right there. And then we have 2 types of random variables. We haven't even talked about continuous. That'll be the next chapter. So we have discrete, and we didn't even cover these 2. So all we care about is binomial. Right? The key to a binomial experiment is that there's only 2 outcomes. You either fail or you succeed. So this could be casted as a binomial experiment. Right? There's 2 outcomes. You either, if you're the bookie, you either win $1 or you lose $5. So this would be success and that would be failure. The probability of each doesn't have to be the same. Right? But the probability of success and failure needs to be the same for every trial. And of course they're independent. Right? The bet I make to the bookie, whether I win or lose, has nothing to do with the fact of somebody else betting with the bookie, whether they win or lose. They don't have anything to do with each other. Okay. That is the spiel, right? So let's look at what's due. So here's our assignments that have been upcoming. Due by midnight tonight is the expected value and the binomial homework. I think after our discussion today, we'll have a little better understanding, especially of the binomial stuff. All right, after I discuss the greater than or equal to things. Showed us how to read the chart. All right, how do we interpret the chart? So your quiz for this, exam 2, this is a really long quiz. You know, when I didn't make, I think all of these quizzes combined are worth 1% of your grade. So each quiz is only worth 0.25%. So if you don't get a great grade on it, it doesn't kill you, all right? And that's why I kind of made them less weighted, is because they're so long. But they're very useful, all right? They're really helpful to help study for the test. If you do well on this quiz, you'll do well on the exam, all right? You're welcome to use your notes on the quiz. So you can't do the quiz after we start the test tomorrow, though. After 9 a.m., you can't do it. So get in there and try it.